For this video, we're going to do a past paper IBDP Math HL graph theory questions. So for this question, we have a weighted graph K representing the traveling cost between 5 customers. That graph has the following adjacency table. The steps for this question are to draw the graph K, then starting from customer D, use the nearest neighbor algorithm to determine an upper bound to the traveling salesman problem. Then by removing customer A, use the method of the deleted vertex algorithm to determine a lower bound to the traveling salesman problem. So let's start by constructing our graph. I can see that in this weighted adjacency table, there are 5 vertices. And so I'm going to start drawing my graph, and I'm going to make it a regular pentagon. Okay, and then I just need to verify the edges and weights. So from A to B, let me add labels to the vertices first. So here's A, here's B, here's C, E, and B. Okay, A to B is an edge of weight 1. A to C is an edge of weight 6. A to D is an edge of weight 7. And then A to E is an edge of weight 4. Okay, on the vertex B, B to C is an edge of weight 9. B to D is an edge of weight 8. And then B to E is an edge of weight 10. Okay, next on the C, from C to D, we have an edge of weight 11. And then from C to E, we have an edge of weight 3. And then the last edge is between D and E, and that is an edge of weight 12. Okay, before we go any further, it's important to note that there are 2 different versions of the traveling salesman problem. There is the classical traveling salesman problem and the practical traveling salesman problem. So based on this graph, we have to identify which algorithm is the one to use. In order to apply the classical traveling salesman problem, there are 2 criteria that have to be met. First, the graph must be complete. That means that between every pair of distinct vertices, there is a direct edge between them. Second, the graph must have the Euclidean property. That means that the weight of the direct edge must be the minimum possible weight that it takes to get between those vertices. So looking at this graph, we can see that the graph is complete. Let's verify if it has the Euclidean property. So A to B has an edge of weight 1, that is the fastest. A to C, weight 6, that is the fastest. A to D is 7, that is the fastest. And A to E is 4, that is the fastest. So far, so good. From B to C, that's an edge of weight 9. However, if I were to go from B to A and then A to C, that path would have a total weight of 1 plus 6 or 7. So that means that this graph does not have the Euclidean property. In that case, we are going to apply the practical traveling salesman problem. So I'm going to select my correct algorithm. Okay, so the first step for the practical traveling salesman problem, since the graph is already complete, we're going to change the weights of the direct edges to be the minimum possible weight. So again, from B to C, the minimum weight that it takes to get there is 1 plus 6 for 7. So I'm going to change the weight of this edge from 9 to 7. Okay, so B to C is okay. B to D, that's 8. That is the shortest. B to E, that is an edge of weight 10. But if I go through A, that total weight would be 1 plus 4, 4, 5. So I'm going to change the weight of 10 to 5. Okay, so all the edges connected to A and to B are the minimum weight. Next, let's look at C. So from C to D, we have an edge of weight 11. Is it possible to get there in a more efficient manner? Well, if I went through A, that would be 6 plus 7, so that's not faster. It looks like I think C to D appears to be the shortest weight of 11. I think that's okay. See the E, that's an edge of weight 3. That looks okay. So then last we have to look at the edge between D and E. So that edge has a weight of 12. Is there a faster way to get from D to E? So if I went through vertex A again, that route would have a total weight of 7 plus 4 or a weight of 11. So I'm going to change the weight of this edge from 12 to 11. Okay, now this is a complete graph with the Euclidean property. That means that now, based on this new graph, we can apply the classical traveling salesman algorithm. Okay, let's go back to the question paper. Okay, so it gave us some instructions for how to complete the step of the algorithm. So it says, starting from customer D, use the nearest neighbor algorithm to determine an upper bound to the traveling salesman problem for the graph K. Okay, so for choosing our starting vertex, we're choosing vertex D. So I'm choosing my vertex here at D. Okay, now that my starting vertex has been chosen, we're going to apply the nearest neighbor algorithm. That means that of all of the edges that are connected to my current vertex, I'm going to choose the minimum weight edge that takes us to a vertex that we have not visited yet. And then at the very end, after I visit all the other vertices, I'm going to take the direct edge back to vertex D. So the shortest weight edge connected to D is this edge of weight 7. I'm going to take this edge, and now I am at vertex A. The shortest weight connected to A is this edge of weight 1. I'm now at B, and the shortest weight edge that takes us to a vertex we have not been to yet is this edge of weight 5. It gets us to vertex E. And now there's only one vertex we have not visited yet, vertex C. So I'm going to take this edge of weight 3. Okay, I visited all the vertices, and now I have to get back to where I started at vertex D. So I'm going to take this direct edge of weight 11. Okay, so as you're computing the upper bound, what you would do is you would add up the weights of all of those edges that we just traversed. We'll see the sum of those weights at the end of this video. Okay, next step, we're going to compute a lower bound by applying the deleted vertex algorithm. Let's see which vertex we need to delete. Okay, it says by removing customer A. Okay, so that means I'm going to take vertex A, I'm going to delete it, and I'm going to delete all of the edges that are incident to A. Okay, now I have the subgraph. So the next step for the deleted vertex algorithm for this subgraph is to apply Kruskal's algorithm to find a minimum spanning tree. So Kruskal's algorithm is a greedy algorithm, which states that at each step, we're going to choose the minimum weight edge that's available, so long as we are not constructing a cycle. So the minimum weight edge is this edge of weight 3. Next minimum weight edge is this edge of weight 5. And then the next minimum weight edge would be this edge of weight 7. However, if I chose this edge, you will see that this creates a cycle between the three vertices B, C, and E. So I can't choose this edge of weight 7. That means that the next edge I need to choose is this edge of weight 8, connecting me to D. When I select this edge, I'm going to have completed Kruskal's algorithm for a minimum spanning tree, and it's important to keep track of the weights of the edges. So far for the deleted vertex algorithm, we have 3 plus 5, it gives us the 8. When I select this edge, there'll be another edge of weight 8 for 16. And now we go back to the original graph. We're going to add back the two edges that have the minimum weight, which we just deleted. So we are at a total weight of 16. The minimum weight edge that was deleted is this edge of weight 1. We're going to add that back. So now we're at 17. And then we have this edge of weight 4, getting me to 21. So then we have computed an upper bound for the traveling salesman problem of 27 and the lower bound of 21. Okay, so that is an example of how to apply the practical traveling salesman algorithm for a past IBDP Math HL exam question.